operating systems that we are going to have is quite a technical course, so it requires us to be a little more serious, so that we can all be able to move together. Okay, so let's begin with our course. So basically, what is operating system? Operating system is basically a software, call it a program, that manages computer hardware. For it acts as an intermediary device. It acts as an intermediary between the users and the computer hardware. So we've used our phones. Our phones have an operating system in them, and for example, most of our phones here are using Android as the operating system. There are those who are using iPhone, which has iPhone OS in it. And then there are those who are using Harmony, because the new operating system that we know currently is Harmony OS, which the Chinese have made. Now, down here we have some logos for different operating systems. This is what we commonly know as Windows. This is around Windows 10 or Windows 11 operating system. Here we have the Mac OS. Here we have the Ubuntu. We have and so on and so forth, Android and so on and so forth. So these are different kinds of operating systems that we have. So when you look at the structure of your computer, we have user applications that we use to interact with our computers. For example, your Word, for example, your PowerPoint, Excel, and so on and so forth. Now, these applications must have an interface which we are calling the operating system. So this one is in the middle. Then now, after the operating system, we have finally what we call the hardware. So without the operating system being there, it is not possible, or it's quite hard for us to interact with our computers. So we have the hardware. Let me use a controller here, pointer. Pointer. Okay. So we have the mechanical hardware. We have it down, and then we have the system software, which in this case we have the operating system. Under system software, we also have what we call the drivers. You know that for you to use your computer, for example, I've seen it when people change operating systems in their computers. You power your Windows, as we commonly say. Initially, if your computer has been having sound, this time around you find that it has no sound. And so they tell you, please, you must put some drivers for what? For sound. So it means even these device drivers are also examples of system software. So now all that is part of the operating system. Then now finally you have the application softwares, where you have your PowerPoint, you have your Excel, you have, and so on and so forth. So the hardware, in this case, can be the CPU, can be the memory, which can be primary or secondary, can be the input-output devices such as the keyboard, such as the mouse or the mice, the speakers, the monitors, and so on and so forth. Now these ones here, to interact with them, we shall need those system, those computer applications, and so we shall also need the system softwares, which we are calling the operating system in the middle there, to act as an intermediary between them. So here are examples of application softwares. I've tried to summarize them here. You have the user, who is interacting with this Microsoft, or is interacting with this email, and so on and so forth. But now this also needs operating system in the middle here. Okay, so you need operating system here, which we are calling the system softwares. Then you have the drivers. You have the drivers. Then finally you have your thing being displayed in your computer, or maybe you have your sound given out, or you have your printer delivering something, or the monitor displaying something. Okay, so an operating system performs various essential functions. some of which include process management. We have they also manage things that we call, for example, memory management. It's responsible for determining how much memory should be allocated to which program, who should receive the first priority of the memory, and so on and so forth. File system management is also one thing that it does. It's able to manage those files for you. Device management, it tells now this device is the one has come in, so it needs the priority. And security. So operating system like now Windows 10 or Windows 11 has what we call the Windows Defender, which initially comes with the operating system, which helps you to protect your computer. I see people using these other antiviruses. They install in their computers, you put your Avast, you put whatever themselves, and they begin disturbing the computer. So Windows Defender is good enough to go when you're using it on your computer. So operating system provides a user interface. It can either be command line or graphical. Command line, you guys have seen that CMD on your computer, and then you can access maybe some of those configurations that you know, or it can be graphical. We see that much of Linux or maybe Ubuntu, much of the operations were initially command line. They're just trying to adjust currently to have things become graphical a bit. But Windows has been so graphical ever since from the beginning. So the operating system ensures that multiple applications and users can operate the computer simultaneously without interference. You've opened your Word, you open your email, you've opened YouTube, you've opened maybe Photoshop, and the computer is able to manage all those things and says this one needs more priority, this one needs more priority at the same time. Okay, what are some of the functions of the operating system? One, the operating system acts as an interface between the user and hardware. It is one of its major functions. It's the middleman between the user and the hardware. Number two, it brings about resource allocation. It determines how resources can be allocated. Who needs more RAM? Who needs more memory in this case? Who needs more CPU to be used, and so on? Who needs to use the CPU at a given time, and so on and so forth. Management of the memory, management of the CPU is the work of the operating system. It also brings about efficiency, conveniency in computer use. So the operating system is very vital as far as our usage in computers are concerned. Types of operating systems, we have the batch operating system. We shall look at them in details. We have the multiprogramming or multiprocessing systems. We have the multitasking operating systems. We have the distributed operating systems. You have the network operating systems, real-time operating systems, time-sharing, and so on and so forth. There are quite many of them. All these things, we shall go through them and we'll see how they work. Okay, these are some of the key concepts we're supposed to know before we can really dig into operating system. These are some of the key things we should know. Number one, knowing the structure of the computer system is vital for us to understand how the operating system works. At least we know how to install operating system. We know how to, play around and maneuver around the operating systems. But now we're trying to dig deep into the brains behind which the Bill Gates and the Steve Jobs, behind which those guys managed to develop these operating systems. What came to their mind? How did they even begin thinking about creating this operating system, and how did they know that this driver should be there for this operating system to work? This is really where operating system gets into the technical bit of it. So a modern computer system consists of one or more CPUs. I don't know how many CPUs your computer has. Mine here has 8 CPUs. So you find that either your computer has one CPU or it has more. And various device controllers connected through a common bus, which provides access to the shared memory. You see, for every device that you have in your computer, it has what we're calling a device controller. So now we're told that input-output devices do not usually communicate with the operating system directly. Your keyboard does not communicate with the operating system directly. Your mouse, your monitor, your disks, your printer, and so on, they don't communicate with the operating system directly. What happens is the operating system manages their tasks with the help of an intermediate electronic device, which we are calling a device controller. So you have your application software that you're going to use. Maybe you're going to access that particular application software using your mouse. The mouse is going to make some commands, but those commands must first go through what we're calling a device controller. The device controller has to interact with the operating system. The operating system finally interacts with your hardware. You understand? So there is that bit of technical thing that is there. For example, the memory determines who receives the resources in a given time. I mean, the CPU determines who receives the memory in a given time. So now, for example, the disks have what we call a disk controller, which is responsible for managing them. You have the USB controllers. Here, your USBs that you have on your computer, maybe one is going to your keyboard, one is going to your mouse, one is going to maybe whatever you connect on it. So now these devices have what we're calling a USB controller. Your monitor has a graphics adapter, which graphics adapter is also a controller. So, you know, these guys were so, I just call them geniuses, to think about this thing had to be there for this particular thing to work. And that's why these days, if you're buying your computers, you want to work on graphics, you must have some dedicated graphics card, which is good enough to handle the motion pictures and all the things you're going to work with. So all the things these guys have to think about them. Now, so you have your application and user. I mean, the user interacts with the applications, the operating system, where you have the system applications, you have your drivers, device drivers, you have the device controllers, then you have your applications. So all the things, so your devices must interact with the device controllers interact with the drivers interact with the operating system finally interacts, gives feedback to the what? To the user. So this is a simple diagram which is a summary of all that. The CPU seeks for the memory and says, okay, the memory, give it to the video controller. He's now working on videos. Give him this memory. And so the memory determines what output you get on your thing, the keyboard, and so on and so forth, using that bus there. Okay, now, examples of device controllers that we have on our computers. Number one, we have a keyboard controller. This one manages the flow of data from the keyboard to the computer in microseconds. You press your keyboard, tick, and eventually the command is given. You wonder how that has happened, but within micro milliseconds, it's able to communicate, and all those steps are there. Have you sometimes tried using, you connect your keyboard on your computer and then it fails to, you press and then nothing happens? It's because sometimes the drivers or the device controller, the drivers are not need to be installed or updated in order for it to work. The mouse, you have tried accessing your touchpad sometimes and the thing fails to work. Sometimes the drivers are missing. So the mouse controller handles communication from the mouse, tracking its movement and button clicks. Every time you move that thing, the device controller or the mouse controller is there to determine how the things are supposed to move. It annoys. Sometimes I've seen someone's computer is touching the mouse and the mouse begins moving without any control to wherever it wants to go. So it means there's some issues with the mouse controller which need to be worked on. Then you have the graphics controller, manages the display of information on the monitor. So you're using your monitor, this is responsible for how the display is going to be. We have the printer controller, controls the printing process, sending data to the printer, and so on and so forth. Sound controller handles the output of sound, sending signals to the speakers or the headphones. Disks controllers manages data transfer to and fro from the storage devices, the drivers, or the SSDs. So it manages how data is transferred from all those different devices. Then you have the memory controller, manages access to the computer memory. You have the RAM there, but it has a controller which is responsible to say, okay, now this person needs more RAM, this person needs less RAM. So then you have the USB controller, handles data transfer over the USB interfaces. Then finally you have what we call the network controller, which facilitates communication over a network. You know, you might have changed your operating system, your Wi-Fi was working, now the Wi-Fi is not working. So, but what's the problem? I have my Wi-Fi card inside the machine, but how come the Wi-Fi is not working? So it means probably you need the drivers in order to have that thing be able to work. So there you have the CPU, which will seek, we have the shared memory down there, we have the bus, which will allow all those different interactions to take place. Then you have the controllers, which we have talked about previously behind there. Okay, so note, this is a point to note. All tasks to be executed must first be loaded to the main memory, which memory we have as a limited resource. Your computer's memory is a very limited resource. No wonder we shall look at the memory structure and you'll see that it is so limited that it's very expensive. So because it's limited, we're supposed to use it sparingly. You have, if you look at how the memory operates, as you give your computer more load, the computer slows down because the memory is fully being occupied. As you free your computer, the computer becomes faster. You know, sometimes you've used the phones and the phone begins to freeze simply because it even tells you, please, no, there are so many programs running, so you have to kill off some of them. So the memory determines how those programs do what, how the memory is allocated to the computer. So to ensure orderly access to the shared memory, we need a memory controller which is provided to synchronize the access to the memory. It determines, give this one more memory, give this one less memory. Okay, let's look at some common terms we shall be accessing along the way as we go through this study. We shall, the common terms, one of them is what we call the Bootstrap program. A Bootstrap program basically is an initial program that runs when a computer starts up. Think about it as maybe a post. In PC repair, we talked about post, didn't we? What is post? Power on, self-test. It is an initial program that runs when the computer starts up. As soon as you power on your machine, that program runs and then it will go to the operating system and tells it, do you have the component which is responsible for starting this machine, and so on and so forth. So its primary function is to prepare the system and to load the operating system into the memory. So this Bootstrap program must run and then it will prepare the system and tell them, okay, load the operating system into the memory. So this program must know how to load the operating system. It must know. And startup execution. And it must also know how to locate the operating system kernel and load it into the memory. So everything has to be there at the right time, in the right place for the operating system to load. That is the whole thing behind this. Now, another term we shall be able to encounter is what we're calling the interrupt. So the interrupt can either happen to the hardware or it can happen to the, so can happen because of a hardware issue or it can happen because of a software issue. However, the word interrupt is specifically used when we're referring to hardware generated interruptions. For example, an interrupt is a signal to the CPU that suspends the currently running process so as to handle a more urgent event, usually from the hardware. You know, when you think about an interrupt, like you guys are standing on a jam, your vehicles are trapped up in jam somewhere, and then even with the jam, the president comes. So when the president comes, it becomes an interrupt. And he says, you guys, you're supposed to go away. They begin pushing you guys towards the, so that he can be able to pass. So, assuming you're using your computer, whenever you insert your flash in your computer, what happens? it sends a pop-up message on the screen. Tells you, please, I need to be given attention. The CPU must give me attention. So according to operating system, that becomes an interrupt. It has been caused by a hardware. You have inserted your flash, and the flash has said, please give me the priority. I need to be used. I have important urgent information which you're supposed to use in a computer. However, if that interruption is caused by a software, it becomes what we call a system call. For instance, a system call acts like a request to the operating system from a program or maybe a software for performing tasks reserved for the operating system. So, a software triggers an interrupt by executing a system call. Think about it like maybe an update. The computer tells you, please, you need to make some update. Please, you need to update. Or maybe all of a sudden your graphics was working, then the display just goes off, and then it tells you maybe you need to update the drivers and so on and so forth. That becomes a system call. So now, these are the things we shall interact with, because we shall be seeing interrupts here, system calls here, blah blah blah. Now, the CPU is always doing something. It has many processes running in the background. Let me show you something here. When I press this, and then I bring this all over the side. When you look at this, is my task manager. It's giving us a summary of some of the tasks that are happening in my computer. Up there it tells you I have my some Google Chrome open somewhere on my computer. It has some 22 processes running. I have my Microsoft PowerPoint running. I have my Microsoft Word, my photos, all the things. Then you have down there, you have the background processes which are running. We look at your task manager. Now, all the things shows you that the CPU always has something it's doing. It is so busy. For you, you may say, but I'm not running anything. But all those processes are able to run in the what? In the background, as you're doing what? As you're using your computer. So you see that. So when an interrupt occurs, the CPU stops what it's doing and transfers execution to a fixed location. Call it the starting address of a given program, where the interrupt is located. As we're studying this course unit, your mind has to be quite attentive, because it's one paper that has always disturbed people, and so you need some bit of more attention. So it says there's what we're calling as soon as an interrupt occurs, the CPU first has to pause, and then to be like, okay, who needs the memory right now, and how much memory does it need? So it gives that, it transfers the execution to that fixed location, and so where the interrupt has been located. So it says, therefore the interrupt service routine executes after completion. The CPU can resume its previous tasks after it has done what the system desires to be done as urgently as possible. Other key concepts of the operating system that we shall be interacting with. One, we have what we call multiprogramming. Multiprogramming in operating system is a method that allows multiple programs to reside in the memory at the same time, with the CPU executing one of them while others wait for the input-output operations to complete. So we have times when the CPU has very many programs which are all in the memory at the same time. So with the CPU executing one, it always has one particular task which has occupied more, which needs more urgent work to be done. So while others are waiting, that's what we can call multiprogramming. So the main goal of multiprogramming is to increase CPU utilization by organizing jobs, code, and data so that the CPU always has one to execute. So under multiprogramming, assuming we have a jam on the road, and then The traffic officer says, okay, now use one way to begin directing to another side. He's trying to see how he can maximize the use of the road, because sometimes you can see maybe the lights have made you guys to stop, but then there are no vehicles coming from the other opposite side. So he says, no, you guys do what? Move and go. So that by doing that, we have what we call multiprogramming in process. So when a program receives input-output operations, the CPU can switch to another program, making efficient use of the CPU time. So this reduces idle time and maximizes throughput. You shall understand what the word throughput means as we go on. So in a multiprogramming system, while one program is waiting for the user input, the CPU can process another program that is ready to be executed. So all the things must happen concurrently. Okay, then we have another term that is often used, what we're calling multitasking. Multitasking is the ability of the operating system to execute multiple tasks, call them processes, simultaneously. There's a difference between multiprogramming and multitasking. Sometimes they tell you the difference between the two. So you have to read through, and then you get to understand it very well. So here we have multiple tasks running simultaneously. Multitasking involves switching between tasks so that users perceive the tasks are being performed simultaneously. It can be divided into two. We have multitasking. Multitasking enhances user experience by allowing multiple applications to run concurrently, such as a web browser, a word processor, a music player, and so on and so forth. When you have all those different tasks happening at the same time, music is playing in the background, you're watching a video. I've sometimes seen that thing, you have your media player is playing audio. Then again, you have a video also playing, and the sounds begin appearing as if, I saw in one device which had such confusion, but usually if the video is playing, the audio has to pause. The sound doesn't, one has to take up the what? Take up the CPU and so on and so forth. So on a modern PC, you can run a web browser, a spreadsheet application, and a media player at the same time. So that is possible because of multitasking in our operating system. Okay. Then we have another thing called throughput. Throughput refers to the number of processes that are completed and their results produced by the operating system within a given period. What this means is, it's basically a measure of how efficiently the operating system manages system resources to complete tasks. So, suppose you have a high throughput. This indicates that the system is effectively managing processes, leading to better performance and faster completion of tasks. Factors affecting throughput include CPU speed, input-output speed, system load, efficiency of the operating system, scheduling algorithms. So all this is possible because if you have your computer efficiently managing system resources and all these tasks are running concurrently and the system is still delivering the best output you can give, that means you can say the computer has a good throughput. For example, in a server environment, high throughput means more requests are processed per second, leading to better performance and user satisfaction. Okay, now you have a computer which has maybe 8 processors. It is handling multiple tasks, and all of them are being delivered at the shortest time possible. The computer is not slowing down. You can say the computer has a good throughput. Popular operating systems, we have Microsoft Windows. This one is basically a series of operating systems developed by Microsoft. We have Windows 10, Windows 11, Windows 8. It's obsolete, no longer. People still use them by that. Windows 7, people still use them. I've even seen people use XP. Till now, they still use them. You have Mac OS, a series of proprietary graphical operating systems developed by Apple for their Mac computers. You have Mac OS Catalina, Mac OS Big Sur, and so on and so forth. Those are all different popular operating systems that you can think about. We have Linux. Here is a family of open source Unix-like operating systems based on the Linux kernel, Ubuntu, which you guys installed last semester. You have the Fedora, you have the Debian, and so on and so forth. Those are all different versions of Linux or Linux. Then you have the Unix. It's a powerful multi-user operating system, originally developed in the 1970s, forming the basis of many modern operating systems. An example is Solaris, AIX, and so on and so forth. Those are all different popular operating systems that we have. Currently, we have Android. This is a mobile operating system developed by Google, based on the Linux kernel, primarily for touchscreen devices. Examples of Android 11, Android 12, 13. I understand even 14 is out. Android 14 is now out. So, Google developed Android, and so because of this, these competitions between China and US, they finally stopped giving Huawei phones. They limited them from using Android, and so the Chinese said, okay, if that's the case, we shall also develop ourselves our own operating system. And so they developed Harmony, which is now, trying to, disorganize Android badly. So Americans thought that the only people who can do the things, but Chinese tell them we can also do the things. I'm waiting to see when Ugandans will develop their own, But for now, we can use what is there. Or maybe for us, we're just consumers, we just enjoy what others have made. No problem. We give them money, don't we? Yeah. So then we have iOS. It's a mobile operating system created and developed by Apple, exclusively for its hardware, and so on and so forth. Okay, I think that is good for the start. Let's look at the storage structure. I have a diagram here, which is a simple summary of the storage structure of our computers. We look at this diagram. We have the registers on top here. You have the cache memory. You have the main memory, which sometimes we call the what? What is the main memory? What is the main memory? RAM is the main memory. You guys. So you launch your operating system and you dropped it wherever. Your PC repair, you dropped it aside. So the main memory is the RAM. Then we have what we call solid drive, but of course this one we can call it electronic memory. Then we have the magnetic disks coming in here. We have the optical disks coming in here. Then we have the magnetic tapes coming in here. What happens is, as the ladder goes upwards, there is increasing speed and cost per bit. There's increasing speed and what? And cost. These hard drives and so on are cheaper. The memory is expensive. Cache is more expensive. Registers are more expensive. So as you keep climbing up the ladder, these things become more expensive. No wonder when you look at your where is that thing of mine? What have I done? Okay, our thing is here. When you look at this diagram of ours here, and I go to my performance on my computer, under the CPU, my computer is quite old. It's an i7 but 4th generation. It's quite old because I've used it from 2015. Now, it has down here, it tells you it has 8 processors, and then it has a cache, L3 cache of 6.0, L2 1.0, blah blah blah. Now, newer computers have this cache increasing, So usually when you're buying new computers, it means you have to consider how much cache does it have. The lower, it means your machine is not going to, it's not powerful enough. I don't know how much your computer has. Who has a better computer here? Have you tried checking these things in your computers? Has anyone tried checking your computers? None? You guys are looking like robots. Okay, so Then you have your memory, which is next to this. You have the memory, then you have your disks come in there, then you have your, and so on and so forth. So, but usually as you buy your computers, we try to check how much memory does it have, because that determines the ladder. So if you have more memory appearing there, that means your computer is good enough to go. Okay, let me cancel off this. Okay, back to our thing. So as you go down the ladder, you realize that the speed also there's increase in size. When you buy, if you're going to buy a hard drive of 500 GB and an SSD of 128 GB, which is more expensive? SSD. But realize the hard drive is becoming bigger, the capacity is becoming bigger, but the cost is less compared to SSD, which is up here, which is smaller, but the capacity, but the price is what? Is higher. So it means there is something special about them. Okay. The registers are a small high-speed storage location within a CPU used to temporarily hold data and instructions during processing. So it means registers are measured in bits. For instance, 8-bit, 16-bit, 32-bit, 64-bit, and so on and so forth. So for them, they are of a high speed. So they are within the CPU. So it means as you're buying your CPU, that's what matters most. What memory does it have? So registers are critical for the CPU's ability to quickly access and manipulate data, which is essential for the overall speed and performance of the computer system. So as you buy your computers, these are the things you first look at. How much memory does this computer have? So we go to the cache. The cache is a high-speed storage layer that temporarily stores frequently accessed data or instructions, acting as a bridge between the CPU and the slower main memory or storage devices. For it, it acts as a layer between the CPU and these other slower memory or running devices in your computer. So it's responsible for temporarily stores frequently accessed data on your computer. Yesterday I was checking on someone's computer there, and when you click on your Photoshop in your computer, for example, you guys know Photoshop. You click on it. The first time you click on it in the computer, if it's the first time you're using it, it will take some time to open. Then you close it. Then you click on it again. It comes a bit faster. Why? Because initially it was not in the memory, it was not in the cache memory. But then later on, the cache memory now says, oh, you just accessed the system a few minutes ago. Do you want to still access it? I still have it with me here. So by the time you click on it, it's able to give you. So now imagine you have less cache memory in your computer. It means the frequently accessed files in your computer will not be able to be accessed quickly. So it means as you buy your computers, those are the things we do what? We check out in your computer. So basically, how does the cache work? When the CPU needs data, it first checks the cache. Says, okay, do you have this copy of the thing here in your memory? Now, if the data is present in the cache, you have a cache hit. It means you have hit the jackpot. It is there. We have it available. Now, it can be accessed quickly. If not, you have a cache miss. You missed, it's not there. So what happens? The CPU goes ahead to retrieve the data from the slower main memory or the storage and also stores a copy in the cache for future use. Assuming I want to access some file which is available in my hard disk, which is inside my computer. And then I also have my external hard drive connected on my computer, which is hanging outside here. Okay? I have my external hard drive, which is also connected to my computer externally, right here. I'm not connecting it, but it's here. Which one do you think will which one do you think the CPU will access its data more quickly? External? Internal. Simply because the internal is closer, is closer to the memory, and so the memory can be able to access it quickly. So the same thing applies to all these to the files which are inside your computer. So the cache will check. The CPU will check whether the cache has the memory. If it doesn't have the memory retained, it will first go to the RAM and check, hey, do you have this information there? Then the RAM will say, no, I don't have it. Go and pick it from the hard drive. Then it goes just like that. So it means anything that is kept within your hard drive will take longer. It takes many more steps to do what? To access the information you should have accessed quickly. So under the primary memory, we have what we call registers. We have the cache memory and the RAM. These ones are primary memory. They're the most important. Then you have the secondary storage devices. Here we have the electronic disks. You have the magnetic disks, optical and magnetic tapes, and so on and so forth. So we have this summary here, which is a summary of all you've learned about storage devices. As you climb the ladder, they're expensive and very fast, but they're smaller in size. And that's why you see my computer just has 6.0 cache memory. It's quite very small, but it's the most important thing. Registers, cache, main memory, which is the RAM. Then you have the electronic disks. Here you find your SSDs, the M2s, which are within the SSDs. Then you have the magnetic disks. You have your HDDs and so on and so forth as you go down. So these ones become larger as they go down, and the cost per bit increases as you go up. For every bit you buy, the cost increases as you go up the ladder. Access time increases as you go down the ladder. You want to access something which is found in your external, it takes more time to access it. Then, on the other hand, these ones are volatile. Registers, cache memory, and main memory are volatile memory, meaning they lose their contents when the power is removed. So as soon as you power off, literally you begin afresh. And sometimes when you power on your computer, everything seems a bit sluggish as you're trying to access the files. Then later on it gains the momentum and then it begins running faster. So simply because now the files are available within clear access time. They're available within the access, they're accessible within our primary memory. So these other ones down here are non-volatile, meaning they retain their contents even when the power is removed. So this is a summary of our input, of our storage devices. Okay, so this is still part of introduction. We're just introducing operating systems as we continue. Let's now go to input-output structures as it is within the operating system. Now, each computer system consists of CPUs and multiple device controllers connected through a common bus. However, each device controller is in charge of a specific device. We saw that clearly. Keyboard has its own device controller. Mouse has its own mouse controller. The graphics, the display on your monitor has its own different graphics controller, and so on and so forth. So, that is to say, each operating system has a device driver in charge of a device controller. You have your hardware. You want to access your sound. The device, you access the sound, checks for the sound controller. The sound controller checks for the sound drivers. The sound drivers checks for the operating system. The operating system checks for the user. The hardware. And then finally, you are able to have your output done what? Given to you. So this device driver provides a uniform interface. Between the device and the operating system. How does the input-output work. Now, operations within the input-output involve the transfer of data between a computer system and the external devices. This can include reading data from the input devices like the keyboards, the mice, and writing data to the output devices such as the monitors or the printers. These operations are fundamental to how a computer interacts with the user and the wider world. Okay. These are the steps that it takes for us to have these operations done. Number one, we have what we call the initiation phase. Here, the process begins with a user or another program, a program request, or another program requests an input-output operation. For example, when a user types on a keyboard, a signal is sent to the computer, or the device controller is sent to the device controller. So similarly, when a program needs to save a file, it triggers an input-output operation to write data to the storage devices. We say, I want you to save this file. But now that file has to be saved into the hard drive. So now it will first trigger and tell the operating system, please locate the device controllers for the hard drive. Then tell it to write this data into the hard drive. So those steps are followed before the device can be able to have the data stored there. So the second phase is the device controller and the buffers. Now, we have. I want to explain what a buffer is with an example of a printer. If a computer sends a command to the printer to print something, the computer's CPU is very fast compared to how the printer is supposed to print altogether. Maybe you are ordering 1,000 copies to be printed by the printer. So now, since we have the CPU is very fast, but the printer is very slow, we have something we're calling a buffer in the middle there, which says, okay, this one eats slowly, but for me, I'm able to determine, I'll receive this, and then I will give it what to eat based on how much it can consume. Now, imagine you're going to have you have two children. One is 10 years, another is 4 years, and you give them the same plate of food to eat food. Who do you think will eat more food? The one who is older, even has more speed, assuming the food is very nice and all of them love it. This one will take more, So now we need a buffer in the middle. So the buffer basically acts as a mediator, and it says, okay, for you eat this, you eat this. This one receives faster, but then it acts as a mediator between the two to determine how this one will receive the instructions. Now, device controllers act as intermediaries between the CPU and the input-output devices. Each device, like a hard drive, network card, keyboard, has a corresponding device controller. These controllers manage the specifics of communication with their respective devices. They also often have a local buffer to temporarily store data during transfers, such that even if the CPU has commanded the printer to print, as soon as it has finished to send that request, for it goes ahead and does other things. Then the printer will now have that memory. It will just keep on doing what? Printing until finally the command is what? The command is the instruction is complete. So a buffer will absorb that pressure and says, okay, I will keep giving you. The instruction was print 1,000 copies. I will keep giving you as the papers get over from the printer. You put other more printers. It continues saying we stopped at 100. So it continues doing that. That's the work of the what? Of the buffer. Now, we have another stage that is involved in this, what we're calling the transferring of data. Here, the device controller receives the input-output request and starts transferring data. Depending on the size and type of data, this transfer can happen in different ways. For example, we have what we call the programmed input-output. Here, the CPU manages the transfer byte by byte, which can be inefficient for large data transfers. So there is transfer of data. And under the programmed input-output, the CPU will try to transfer the things byte by byte. However, it's not convenient for files that involve large data. And so because of that, we have a solution which we call the direct memory access. Sometimes you want to transfer some heavy things, but those heavy things you're going to transfer may not be able to be accessed by the CPU directly. And so because of that, we have an alternative whereby the CPU will go and access the things from wherever they are stored and brings them. So a DMA controller handles the data transfer directly between the device and the memory, freeing up the CPU for other tasks. Because under programmed input-output, the CPU itself is responsible for the transfer of data. But under direct memory access, here the CPU is released. The memory will access the data from wherever it is stored and brings it to the what? And brings it to be executed, freeing the CPU to handle other things. So data can be transferred to and from the device through the device controller's local buffer. Okay. I think let's finalize. The things are becoming too much. Finally, we have what we call interrupts and direct memory access. Still explaining that, we say here it says that once the data transfer is complete, the device controller signals the CPU via an interrupt and tells it, please, the thing is done. Interrupts allow the CPU to be notified of events without constantly checking for them. In case of large, you've tried to download the file and maybe the files were so heavy and you didn't want to keep looking at it all the time, and then later on when it is done, it sends you a message down there and says, download what? Complete. So that work is being done by the interrupts are able to notify you about all the things as they're being done. So in case of large data transfers, direct memory access may be used, allowing the device controller to transfer data directly to or from memory without the CPU's direct involvement. Then finally, we have the CPU interaction. Here, the CPU handles the interrupt, potentially processing the data that was transferred or initiating the next step in the operation. The CPU then returns to its previous task or continues the input operation if it is necessary. So, in the conclusion, the input operation is considered complete when the data has been successfully transferred or processed and the device is ready for the next operation. Assuming you're transferring data from an external to your computer, and then the external checks, what happens? Even what initially had been copied, assuming if it was 99% and it has failed to reach 100, what happens? Do you have that memory stored there? No. So it means there's no way you can receive a completion notification that indeed the thing has been completed. So the same thing applies to how these operating systems work. So examples of input-output operations: you have the keyboard input. When you type on a keyboard, the keystrokes are sent to the keyboard controller, which then sends signals to the CPU via an interrupt. The CPU then processes the input, e.g. displays the character on the screen. Okay, assuming you're saving a file, when you save a file, the application sends the data to the storage controller. The controller writes the data to the hard drive and signals the CPU when the operation is complete. Assuming you're having a network communication, when you visit a website, your browser sends a request to a web server. The server then sends the website data back to your browser through a network controller. So here we have the summary of how that is done. For most devices, the CPU can access the information directly from the device. But for large devices, we have an alternative using the direct memory access, where the memory accesses data directly from the devices, so that they can free the CPU from having all that headache. Because sometimes the CPU has a lot of things, it becomes so overloaded, and then operation, the machine becomes a bit slow. Okay, in summary, to start an operation, an input-output operation, the device driver loads the appropriate registers with the device controller, within the device controller. The device controller in turn examines the contents of the registers to determine what action to take. The controller starts the transfer of data from the device to its local buffer. Once the transfer of data is complete, the device controller informs the device driver via an interrupt that it has finished its operation. So the device driver then returns control to the operating system and notifying that everything is complete. I think let's stop here. Let's stop here for today.